Today in class, we talked more about work and what that means with regard to energy. And I'm going to start this by saying again the conceptual argument I said at the beginning of class, so that hopefully that will help you in thinking about work and energy and forces and how those are all related conceptually, so that you can deal with that along with the mathematical relationships we've been talking about and how those things are related. Remember, forces cause accelerations. An object will change its behavior with regard to its motion, its speed or direction, if there is a net force acting on it. So, an object will have a state of being at rest, or it will have a velocity, a specific speed and direction, and it will keep either the state of being at rest or the constant speed and direction unless acted on by some outside force, which then causes it to change its behavior, to change its speed, to change its direction. That changes the energy of the object. It will either give energy to the object, or it will take energy away from the object, or convert it into a different form. And if the force in question that is changing the object's behavior acts over a specific distance, then that will give the work. So work is done on an object by something if a force is changing its behavior in a certain direction. So if we talk about a box that's sitting, just sitting, doing nothing on a table, okay? It has, if this is a table and this is the ground, it has potential energy right now. The gravitational force is acting on it. It is in the downward direction. The force from the table is supporting it, and it's pushing up. However, while these forces are both acting on this box, the box is not moving. So, these forces are present, but there is no work being done on the object by these two different forces. Mathematically, that says that F times the displacement is going to be 0, since the displacement, which in this case would actually be delta y, or delta x. But if we're talking about the force in the same direction, the direction in the same direction as the force, then as delta y, it's not moving. Its behavior is staying the same in relationship to this direction. And so therefore, the work being done by those forces is 0, because those forces are not changing the behavior of the object, of the object's motion. It is staying the same. Now, if I come along and I push it with some force F, and it moves across the table a distance x to the edge, then I have done work on the object because I have moved it. I have changed its behavior. I have pushed it a certain distance. And so I know the amount of work that I've done in that object, W, is equal to my force times the displacement times the cosine of the angle between my force and the direction, which in this case would be 0 degrees. The cosine of 0 degrees being 1. So I have given the object energy. What energy have I given it? I've given it kinetic energy, because now it's moving, it has a speed. It still has the same potential energy it had before, but I've given it extra energy kinetically, and in that x direction as opposed to the y direction. I have done work on the object to change its state. I have changed its behavior. I have physically done that. Now, if there's friction that is involved, then that is going to be also acting, but in the other direction. And you can talk about the work being done by friction, and that, instead of being positive, would be negative. I am giving energy to the object. I am doing positive work on it. Friction is acting in the opposite direction. It is taking energy away from the object. It is resisting the change in the object's behavior. It doesn't want the object to change behavior. So it does negative work on the object, taking energy away from the system. If my force equaled the static friction force, I couldn't move it. The amount of work that I'm trying to do would equal the negative work that the friction is trying to do, and so therefore no work would be done at all. And you would have a state where the behavior does not change, the state is the same. So, forces cause changes in behavior. Work is a way to talk about the amount of energy that goes into changing the behavior, and therefore the amount of energy the object gets, or the energy the object loses. And we write that down mathematically by saying that any work done by non-conservative forces is equal to an object's change in kinetic energy and its change in potential energy. Where the potential energy, you'd have to think about all the different things involved in the system that could actually store energy. The only ones we talked about so far are gravity and springs. So pushing a spring down or pulling a spring up, storing energy in the fact that it wants to go back to the state that it was at. So we have those two different types of potential energy that can be set up. And so any kind of work you're talking about is related this way. This is, if you remember, this would be negative the conservative work, where the more general equation is non-conservative work plus conservative work is equal to the change in kinetic energy. So, if you only have conservative forces, meaning that they don't change the overall energy of the system you're talking about, and you don't have any friction, so this term would be 0. So if W and C equals 0, then you have the kinetic energy change is equal to the work done by those conservative forces. So, work done by gravity, or in moving this eraser down to the ground, has converted the potential energy up here into kinetic energy, or it's caused the change in kinetic energy from 0 to what it is at the bottom. Gravity has done work on the object to give it energy, to change its state from kinetic energy to kinetic energy of 0 to kinetic energy of a number at the bottom. Okay. That is what has happened. There has to have been a force that was acting on it, and that would be the force of gravity in that direction. It just so happens that the gravitational force is conservative, and so all of the energy that it had up here in the form of potential energy becomes kinetic energy at the bottom. And that's why we can talk about it in terms of this way. And we can write, if there are no non-conservative forces, so if the work done by them is equal to 0, then we have the statement that 0 is equal to delta KE plus delta PE. Or, also, that that's the kinetic energy final minus the kinetic energy initial plus the potential energy of all forms final minus the potential energy of all forms initial. Or, if I bring the initials on this side, like I did last time, then I have the total amount of energy you have beforehand, whether it be stored in a spring, stored in the position above the ground, or present because the object is moving, all of that energy has to show up in different forms in terms of either storage in springs, storage in height above the ground, or the speed of the object afterwards. All the energy that was there beforehand has to equal all the energy that is there afterwards in terms of these mechanical processes and conservative forces we're talking about, as long as there is no non-conservative force like friction, air resistance, thermal heating, internal processes, things like that. That would take energy away from the system. But if you're just talking about a solid ball that has no vibrational states that can be thrown up into the air and land on a spring and bounce back up, okay, then that is what we're talking about here. So the energy before has to be equal to the energy after. Now, even if we do have a non-conservative force, that still shows up in the energy equation. And that means the energy has has left the system. Or it has entered the system, depending on if something has given it energy. If some non-conservative force has given it energy. So, WNC is equal to, if you write this out, is equal to the final energy minus the initial energy. If WNC equals 0, then the energy final equals the initial energy. If it doesn't, then the difference here in energy is due to the work done by some non-conservative force, whether it be negative or whether it be positive. If the initial energy is smaller than the final energy, then the non-conservative work done has been positive. And that means that the system has gained energy from something that has acted on it. Now, if the opposite case is true, if the initial energy is bigger than the final energy, then the work done by any non-conservative force is negative, and so energy has been taken away from the system. But the energy is all accounted for, because we would know where this energy went. We would know that if it's negative and it's left the system, it's gone into something like heat between the two surfaces, if we're talking about friction, or between the air molecules and the object, or it's gone into creating sound, or it's gone into creating light, or it's gone into making electric current, something like that. All the energy has to be conserved. That is one of the major tenets of physics, that energy can't be created and it can't be destroyed. You cannot just get rid of it. You can only transfer it and convert it between different forms. You could even change it from matter into energy. And that took us, if you remember in class, onto a tangent with regard to black holes and antimatter and regular matter. But that was beside the point. So, what we're talking about now is analyzing everything with regard to the energy that it has and the form of energy that it possesses, that shows up as. It could be kinetic energy, it could be potential energy, and it could be energy that leaves the system because of some force that's non-conservative acting on it, or it could be gaining energy because of some non-conservative force acting on it. Okay? And just to remind you what these forms are, we have the kinetic energy equal to 1/2 mv², so it depends on the mass of the object and depends on the speed of the object. The potential energy of gravity is equal to the mass times the acceleration due to gravity, 9.80 meters per second squared as the average, times the height you are above some 0 point, which we usually take to be the ground, but you are free to define it wherever you want to define it as long as you are consistent. You can call that y instead of height, depending on how you want to do it. And the potential energy stored in a spring has to deal with the spring constant, which is a property of the spring, how stiff or how flexible the spring is, times how much the spring has been stretched or compressed. So x would be that difference from the equilibrium point. And if you compress it a certain amount, or stretch it by that same amount from the equilibrium point, you store the same amount of energy. The resulting motion will be different. If you compress it, it wants to go up. If you stretch it, it wants to go the other way. But the amount of energy you store would be the same, since that x right here is squared. Okay, the potential energy will be a positive number here because of that. Just the direction of the resulting motion will depend on the direction of the force that the spring is exerting on this object, and that would depend on whether it's being stretched or whether it's being compressed. Energy is a scalar. Energy is a scalar. But forces and accelerations are vectors. Okay, that's an important thing to remember. And that's why when we treat things as energy, we don't have to worry about the components of stuff as much as we do when we're talking about accelerations and forces, where you have to analyze things in terms of the different directions. Okay. So, while you're thinking about things for the exam on Tuesday, try to keep this broad picture in mind, because I may ask you a question conceptually about this stuff, along with the other parts mathematically that we've been talking about for the last number of weeks.